Hi, in this video we give the solution to 3 problems of the first module. In that module we gave 3 problems about the applications of curves on constructions and architecture. These problems were the best supporting arc, the best freestanding arc, and the optimal shape of a beam. With respect to the first problem, we are looking for an arc spanning a space and supporting a weight above it. This weight is uniformly and linearly distributed. The ideal example is the arc of a bridge supporting a road above it. Best arc, or optimal shape in this case, means that the tension or supporting force transferring the weight from the bridge to the ground is always tangent to the trace of the arc. We now consider a piece of the arc from the top to a point at distance x, and we draw the forces. At the top point, the force is horizontal, and we decompose the tangent force at the right point into horizontal and vertical parts. The balance of forces at that point means that the horizontal part of the force of the right point equals T0, whereas the vertical part is the weight of that piece of the arc that is proportional to the distance x. We look now for a parametrized curve of the type the graph of a function f, such that the force we computed before at point x is proportional to the derivative, that is proportional to the tangent vector. This implies that T0 and the derivative of f equals minus mx. We need to find a function satisfying that relation. Solving for f prime, it equals minus m over T0x, and it's easy to find a function satisfying that equation. It is a quadratic polynomial, and its graph is a parabola. The parametrization gives a parabola as its trace, and the constant depends on the mass density and the force at the top point. There are many constructions illustrating this problem. For example, this bridge over the Duero River in Spain. And this problem also applies when the arc has to support the bridge below it. And this is the case of the Golden Gate in the United States. The parabola is on top of the bridge. The second problem is the freestanding arc. It is a very similar problem. In this case, the arc just supports itself. Now the weight is proportional to the length of the arc. The proportion is not with respect to the horizontal distance, but with respect to the length. L meters of length weights ml kilos. Again, we consider a piece of the arc and we decompose the horizontal and vertical parts of the forces. The balance of the forces for that part of the arc says that the horizontal part of the forces at the right point is a constant, whereas the vertical part is proportional to the length of the arc. Look for a parametrized curve of the type the graph of a function, satisfying that the force computed in the previous slide is proportional to the derivative, that is proportional to the tangent vector. Mathematically, this implies the condition at the bottom of the screen. We have to find a function satisfying that relation. We recall that the length of a curve can be computed with the integral on the screen. These two equations are put together in this equation at the center of the screen. And to make it easier, we compute the derivative at both sides of this equation. We have to find a function satisfying this relation. This equation is not easy to solve, but at least is not complicated to check that the next function is a solution. The graph of this function is a catenary. That is, we have a parametrization of a catenary with a constant depending on the mass density and the force at the top point. There are nice examples of these catenary arcs. For example, this famous arc in San Luis, the United States. And the same principle governs the behavior of a hanging chain or cable, as for example this electric power cable. And finally, the optimal shape of a beam. We have a beam made of a more or less elastic material, and we look for the shape of that beam under some initial and final conditions. These conditions are a point and a direction, the point A, and another point and another direction, point B. The distance between these points must be less than the length of the beam. This is the so-called elastica problem and involves very complicated differential equations out of the scope of this course. However, the principle governing these equations and the solutions is simple with the language of curves that we have studied in this course. Leonhard Euler and Jacob Menouilly gave in the 18th century the principle for thin lines, that is, lines where the torsion is not important. This principle is as follows. The shape of the beam with these initial and final conditions minimizes the integral of the square of the curvature. This integral is called the deformation energy. But for that, we consider that the curve is parametrized by the arc length parameter. If not, the integral must contain another factor, the modulus of the derivative. In other words, we have to minimize the deformation energy. For thick beams, that is, when the torsion cannot be neglected, the optimal shape also minimizes an integral, but in that case it is a combination of the square of the curvature and the torsion. The coefficients of that combination depends on the material of the beam. This is again when the curve is parametrized by the arc length parameter. This deformation energy must be minimized. There are many examples of this situation. On the screen you have the wooden beams of the roof in Terminal 4, Madrid Airport, Spain.